Every minute of every day, a security force patrols your bloodstream. These are your T cells, whose mission is to eliminate foreign threats. Cancer, however, is a highly evasive enemy. It creates a harsh, toxic environment that forces these patrolling immune cells into a grinding war of attrition. This chart illustrates the biological toll of that war. The steady line shows the energy level of a healthy T cell. But inside a tumor environment, its internal energy reserves rapidly crash to zero. This is T cell exhaustion. Adding tumor volume to this same graph makes the consequence clear. The moment the immune cell's energy bottoms out, the tumor size surges. The primary roadblock for modern medicine lies beyond simply mobilizing an immune army. The true hurdle is preventing that army from dying of exhaustion once it reaches the battlefield. Solving this exhaustion problem required scientists to look past the macro battlefield and peer deep inside the architecture of a single failing cell. What you are looking at here is an isolated mitochondrion. It acts as the cellular power plant, generating the precise energy a T cell requires to function, move, and fight. Deep inside that power plant sits a specific molecular regulator, the ANT2 protein. Its normal biological job is to keep the cell operating in a calm, steady baseline state. This schematic maps the mechanism. Deactivating this central ANT2 node instantly triggers a cascading chain reaction across the organelle. Without ANT2 regulation, the mitochondria alter their energy metabolism, adopting a new, highly efficient metabolic loop that continuously cycles without depleting. Inhibiting this one protein changes the T cell's metabolic architecture for generating and consuming energy. When you compare a standard baseline T cell against this modified ANT2 disabled version, the physical combat upgrades are stark. First, the reprogrammed cell exhibits hyperaggression. It attacks cancer targets with more physical force, initiating a rapid attack sequence to dismantle the tumor structure. Second, it gains extreme endurance because its new energy loop never runs dry. The modified cell survives for extended periods inside the toxic environment of the tumor without suffering from exhaustion. Third, these cells can clone themselves at accelerated speeds. They multiply rapidly to form a massive precision-targeted swarm right at the site of the cancer. By inhibiting this protein, the immune system transitions from an easily exhausted defense force into a persistent, high-intensity strike force. Moving this discovery from laboratory cell biology to real-world clinical application requires a practical delivery mechanism. One method to disable the ANT2 protein is direct gene editing, but altering a patient's DNA is a highly complex and resource-intensive procedure. This flowchart compares two delivery methods to achieve the same result. On the left is the complex genetic path. On the right is a second breakthrough. The exact same cellular reprogramming and ANT2 blocking effect can be triggered using a simple pharmacological drug. Delivering this mechanism via a pill makes the treatment far more scalable. It moves the science away from expensive, customized therapies and toward a clinical defense that is accessible and affordable to the global population. The discovery of the ANT2 regulator provides a clear biological blueprint to bypass cellular exhaustion. It lays the groundwork for a new generation of immunotherapy that tips the odds in humanity's favor against cancer.